Yeah, so I'll just start in a minute. I don't know why people are not joining. I think at least two more people are supposed to join. Chalo, we will start. It's not delay. So, where is the pen? Just, yes. Okay. So let us start with the review. Let us start with the review of what we did the last time, right? So that we can put things in perspective, and also we'll see if there were any gaps to fill and so on. Okay. Review of last class. It was last Sunday. Yeah. So we were trying to discover the formula, right? Or we proved, rather, I would just say we proved the formula and choose R, right? We proved that this is nothing but R factorial n minus R factorial. Yeah. This is obviously choosing R people from N people. Yeah. It looks like a very specific formula, but it's very, very general. Okay. So that's a very important feature. Okay. It's a very general formula. It looks like, okay, it's a formula for choosing R people from N people, but it can be used, or it will be used in so many unrelated places that it's really, really fundamental. Okay. So very general formula in the sense that it has a very wide applicability. Okay. Wide applicability. In fact, this C is more like combinatorics, or rather enumerative combinatorics. Very wide applicability. So we proved that from N people, if you want to choose R people, then there are many ways to do it. And that number can be written in terms of products in this manner. Okay. So this is something that we proved the last time. However, the technique we used proved using, so can anybody say what was the method we used to prove? What was the approach? We took a slightly non-traditional approach. Can anybody mention or describe even better? So what was the approach? That's right. That's right. That's right. Yeah. So maybe I should say it better. I should say that we actually proved this, which is the same thing, but still this is the way we proved. Yeah. And then that's exactly the way you said. This is what we actually proved, right? From m plus n people, if you want to choose n people, then this should be the formula. But these two are the same things, right? From n people, so you can write this n as, it is the same thing. You can write this n as n plus r minus r, and you can see, or rather I should say, you can write this as n minus r plus r, right? This becomes the m, this becomes the n, and then you're gonna say same thing. Okay, so these are the same formulas, but this is the way in which we actually arrived at it, and exactly we did it using a slightly different way. We proved this using the model, okay, using a number of paths. Now this path is understood, the rules we know, either you move to the right or you move up. Number of paths from let's say 0, 0 to m, n. Yeah. I don't know, maybe there was some problem in the way I sent the mail. Did people not get it? I'll just check once and then I'll continue, okay? Okay. They're in the same mail chain, so yeah, okay. Yes. Start, continue. So this is the model we used. Okay. So let's go a little slow today because there are only two of us. Let's try to understand things more better. So in a sense that have a more question and answer based class. Let me ask this question. Okay. Find the number of, it's just simple exercise. Find the number of ways. This way we can review. So number of ways or number of paths, rather, same thing. Number of ways to go from 2,3. Now 2,3, you guys understand, right? 2 steps right and 3 steps up. From that point, I'll also draw it to, let's say 5,5. Or let's make it a little more interesting, 5,7. Okay, let me just draw it so that it's, and then you can think. 0, this 1, 2, 3, 4, 5. And like this it goes. Yes, 2 more. So it will be somewhere like this. This will be 5,7. Yeah, this will be 5,7. So that's 5 steps to the right and 7 steps up. And this is 2,3. This is 2,3. So now we don't want to go from the origin, but we want to go from this point to this point. And how many ways are there to go? Everything else being the same, meaning that, you know, you can move 1 step to the right or 1 step up at a given time. Yeah. Yes, right. So we have to move, as you said, 1, 2, 3, 3 right and 4 up. Someone just said, yeah. So that's perfect. Yeah. So we have to move 3 right and 4 up. So 3 rights, 3 rights, 3 rights and 4 ups, right? So then what should be the way? What should be the answer? 3,4. No. Yeah. So what will be the number of ways? Yes. What should be the number of ways to do this? Yes, exactly. Right. So you can just apply that formula. Okay. So that is certainly correct. So this will just be 7 choose 3. Okay. Just like we had done m steps, if there were n steps right and m steps up, that was the essence of it. This is the same problem, but just it is translated in a different place. Okay. So that's right. But you must also not forget the method in which we have done it. So if you are in an exam and if this is suppose, just saying, if suppose this is a 4 marks question, something like that, you know, just then you can just explain. Yeah, you can just say that this is 3 hours, this is 3 hours and 4 U's, and you want to arrange them and so on, which we had discussed last time. You can go into the details if you think it's needed in that context. I don't know, it depends on the level of the exam and so on. Okay, so just, so this is just the same thing. Okay, so right. So this is what we did in 2 dimensions. Okay, now I want to go to three dimensions and ask the similar question. Okay, but before that, let me ask a slightly unrelated looking question, which is quite related actually. Okay. A number theoretic, number theoretic application So let's just see. So let us just do this experiment. Okay, let's just start with, let us just start with any number. So any number, let's say n equal to 31. Yeah, starting with 31. Okay, now let us take any small number. It doesn't matter, we can take big also, but take any small number. Let's say 5. Okay, now what I'm going to do is, from 31 I'm going to take 5 consecutive numbers. Okay, 5 consecutive numbers including 31. Okay, so 5 consecutive numbers starting with 31. So what will they be? 31, and then I'll multiply them. 32, 33, 34, and 35. Okay, now let's see if this is divisible by 5 factorial. Okay, let's just call this k. So is k divisible by 5 factorial? Think about this, or just check it. You guys can check this independently, it will be good. And then, so 5 factorial is 120, and you can just check if it's divisible. I just want to know if it's divisible or not. I don't want to know the answer of the quotient and such. Okay. Yes, all the numbers are there. You can break it and check. That's right. So it is, yeah, yes. So the answer is yes. So here I have taken 5 consecutive numbers and I've divided it by 5 factorial and it is divisible. Now, just take a minute, or however fast you can do, think of any think of any number, take 6 consecutive numbers from there. Don't take 31 only, take some other number, maybe 6 consecutive numbers, and check if it is divisible by 6 factorial. Okay, just try this independently so that, then you can share what you have done. And so do the same with 6 consecutive numbers. Okay. Take a decent, don't take very small number, take a decent number. So what was the number you took? Okay, so this is checked. Okay, so Pragya, have you checked with some other number? Yeah. How could we explain this? Why is this happening? So, okay, so first of all, do you guys have any explanation for why this is happening? Then we'll try to formalize this mathematically and then say, but why do you think this is happening? Yeah, seems like a very strange, or is it strange? Can you give some kind of an explanation? Like, I'm not saying a proof. If proof you can give, that's the best thing, but some kind of a justification. as to why such a thing would happen. Hmm? That is okay. Okay, that seems most numbers. Yeah, so this can be a little bit of a justification so that the result is not that surprising. Yeah, most numbers among the consecutives are not primes. Okay, this is something. Yeah, to just explain as to okay, so this is not a very surprising phenomenon. Yeah. Okay, but still, like anything more we can say, which is more of a causation. Yeah, this is maybe a little bit of a maybe correlation, some kind of okay. Yeah, these phenomena and that they look similar, they kind of support each other, but more of an explanation. Let's think about this. This is a very major result. Okay, this will be a very useful result. But in fact, it's very simple to prove. So the maybe as a hint, I can just, if I can call it, the answer is on the board. It's somewhere on the board. It's there. And also, if you want to try to formalize the observation. Because if you formalize this observation, then you can take the help of, I mean, then, basically you can take the help of maths more. Yeah, of the things that we have seen or you have seen already. Formalize the observation and try to prove it. Or you can directly do something. So as a first step, let's try to formalize the observation. Can anybody try to do that? So like formally, if I want to state what is happening, like we all understand what is happening, but we want to, let's write one sentence that we can all agree upon and anybody else would kind of agree, meaning that they can check it. Yeah. N consecutive no, yeah, so you said the opposite a little bit, but yeah, so yes, right, yeah, so let me not say N, let me say R maybe. I mean, I could say N, but I'll use, or yeah, we can take N only, yeah. So N consecutive numbers, N consecutive numbers, and this is a very good theorem in number theory. It can be proved by other ways also, induction and all is also there, but this is what we'll see will be a more direct proof, and it will be one of the results of the type of results that is to come, that is proving number theoretic facts using combinatorics. Okay, so N consecutive numbers is divisible by N factorial. Okay, so again, can anyone can try to formalize this further? Can you further try to make it more, like, can you write it in the form of equations or in the form of numbers, and as a, oh no, M star, yeah, okay, that's right, yeah. But since I've already taken N here, so let me just start with M, and yeah, so yeah, so let's start with M, and let me end with, since I want to end with M plus N, I don't need to, but for a certain reason you can see, or let's not do it. Let me not be artificial. Let's just do it as if you were doing it, the way you would do it. So you see, writing it like this, suddenly starts to, because see, we do not understand mathematics. We don't understand. We don't understand everything equally deeply, right? In maths. I mean, that's the reason why we have theorems and we have lemmas, and because we want to stand on the shoulder of giants and we want to move forward. So that's why it's always good to rewrite your thoughts in first maybe words mathematically, and then in terms of equations if needed. Okay, obviously it has to go back and forth between them, but this can just assist you. It can just make you spot something which you may otherwise not. Okay. So starting with m, so that's again some new variable we have to introduce to write it. If you go up till, you have to go up till m plus n minus 1, right? This will be the nth number. Okay, because we're starting with m plus 0. So that's okay. That's right. And this divided by n factorial is an integer. Is an integer. What integer is it? So it's a very special integer. Please tell me what integer it is. Think. It's an integer. This is the claim. This is the claim, right? This is the formalization. This is the final formalization for our requirements. Obviously, now if you need to write it in a computer, you need to formalize it further. Or if you want to type it in LaTeX, something like that, that will formalize it further. But it is enough for us to understand and use the language. What integer is this? So this is already there on the board somewhere. So if you play around with this expression and simplify this, or yeah, so I can say two things. Okay, so now, right? So now I try to complete it. I'll not. So this will be interesting for homework. Okay, so these two are very related. Just do it. See, these things are obviously formally done in the books. Even in NCERT, it's formally done, but maybe they don't prove this result. I don't know. But the simplification of this is just a very routine thing. Okay, so these two are the same things, are same, not same, but similar. Try to relate it and finish the problem. Okay, finish it. You see, it's very surprising, right? This is an integer. So and something being an, I mean, in the end, it's fine. We understand it, but it's a very interesting coincidence that something proving that something is an integer is usually a matter of primes, right? And it has all the primes and so on. But it turns out that the easiest way to do it is by interpreting this as counting something. This is counting something. Okay, this is basically counting something. So I mean, one can say it more directly even without using this, but that will, maybe you can also think about that. But this is counting something. And we will see a lot of results like this over time, and you will also encounter them and in tests and other places online and so on. It's counting something. That you see an expression, and especially if it's products and so on, and you do not have a number theoretic way to approach it, then maybe you can think of, okay, let me think, does it count something? Okay, or maybe try to manipulate it and write it in terms of n choose r and something like that, right? And then you will be able to somehow prove a number theoretic fact using combinatorics. Okay, there will be other questions like this, but let's not discuss all of them in one at once. Maybe slowly we'll discuss the harder ones later and some for homework, so on. No. Yes, right. They are not the same. Yeah. So if you work it out, you'll see this will actually become m plus n minus 1 choose n. check it yourself. Don't believe me. Okay. Try to finish it and understand. Yeah. It's not the same, but it is similar. Yeah. It is something, choose something. So it should be an integer. Right. So it's a very interesting way to do things. But usually it can be done by induction also. Okay. So yeah, let's see what I want to do next. Yes. So as I was saying, we want to now do the same problem in 3 dimensions. Okay, because that will help us to discover a different kind of counting question. These are also called binomial coefficients. Okay, they're also called binomial, and the reason you will see very clearly soon. Okay, I am not discussing it today, but I mean, for if you've seen binomial expansion, then also you know, but otherwise also we'll explain. This is also called binomial coefficients. But now we will do a 3-dimension version, which will help you to discover multinomial coefficients. Okay, but we don't need the words, right? Those words right now. 3-dimension analog. Of the path of the lattice walk problem. So yes, so let's draw a 3-dimension image. 3, obviously, when you're drawing, it's just a perspective. So this will not be hard at all because you've already done the work. It is very, very similar. It will be as far as an analog. So first of all, see, in 3 dimensions, there are 3 directions here, primarily. So there is a X. So let me just calling this X, this direction. This direction is X. So this, and then there is a second direction outward. So maybe I could have taken this to be parallel to the screen or something like that. And this outwards, this is a Y direction, and this is the upward Z. Now, don't think that this needs 3D coordinate system and so on. No, just think of it as your room and just, how much up you are, how much in this direction, how much in this direction, and how much in this direction. That's all. There's really nothing else here. Okay, suppose again, I'm just starting at here 0, 0, 0. And I want to, let's say that, let me just write it. I move, let's say, 4 steps in the X direction. Okay, we can actually just take all to be 4 steps, then 4 steps in Y direction, right? And 4 steps in Z direction. So there are these 3 directions I'm moving. So previous version, it was only 2 directions. Now there are 3. That's the only difference. Okay, so you move 4 steps like this, come here, and then you move 4 steps like this, come here, and then you go 4 steps up. So is this the right perspective? Okay, then you go 4 steps up. 1 second. Sorry. Then you go 4 steps up. So the place where you come finally, I just call that 4, 4, 4, because yeah, the first 4 is how many directions in the X, and similarly Y, and similarly Z. Okay, these basic coordinates you can understand, like, okay, yeah, this is because you may need this even in these. It's a good way to think. Even if coordinates are not there, geometric shapes, you can use this. Okay, anyways, this is where you are. Okay, now the question is, see, now how many ways are there to get here from 0, 0, 0 to 4, 4, 4? Obviously, this was one way, this pink path, but then there will be many other ways, right? So find the total number of ways. That's right. Yeah, find the total number of ways, find the total number of ways. From here, we want to go here. Okay, so obviously, so at each step is either in X, Y, or Z direction, not any other. You can't walk diagonally. Okay. Yeah. So let's think. Yeah. So you guys can think about this. Just try to draw the picture. Yes, that is certainly the correct answer. Yeah. So that is certainly the correct answer. But yes, and that's a very uh, reasonable guess also, if it's a guess. Okay. But then let's see, how can you explain it? That is a question. In some sense, we are, but you have to say more details for one to believe. Because why is applying the formula twice the correct thing to do? One has to still prove. Yeah. And so on. Just goes on. Why? So this is certainly the answer. It's a right guess, but why? Okay, that's right. Essentially, we just want to permute them. Number of ways to permute. Yeah, so you see again, this problem is just number of ways to permute 4x's, 4y's, and 4z's. But now there are three kinds of quantities. How do we, yeah, how do we find the answer to this? Why is this the answer and not something else? Yeah, so it is correct that we need to take 4x's, 4y's, and 4z's, and we want to permute them. And that is exactly what the question is. But yeah, then. So again, as an analog, it is correct. The answer is reasonable. It's what it should be. But how do we explain it? So it is, in the end, it is something like applying the formula twice. Okay. So maybe you can take that as a hint and think about this. Maybe I'll also draw the spaces. So there are 12 spaces. So last time to answer this question, we went from permuting to choosing somehow. So maybe you can think of that again. Mhm. Uh-huh. Okay. But okay. Yeah, this will be 8 factorial by 4 factorial times 4 factorial. Yeah, because it's just two. Yes. Yes. But then we can't, but then what do you do with all of them? You can't add them, right? Because usually the paths will be very complicated. They will not go to 4 comma 0 comma 4 or 4 comma 4 comma 0 and so on. They may take some other strange journey. It may go like this, may go 3 steps here, then it may just go up. I mean, it won't reach by just going up, but it will go up all the way, and then maybe it will take the rest of the steps like this, and then yeah, then it will reach here. Hmm. No, but how many points? That is easy to find, but that will not be. How will that help? Which point? Yes, yes. But yeah, but yeah. So here we have to go from 0 comma 0 comma 0 to 4 comma 4 comma 4. So then what is? So you're saying something different. So we need to go from this point to this point. We know that already. In the x direction, yeah, this thing we know. That's it. And we just want to now we just want to arrange them. Yeah. We just want to see how we can permute these. Yeah. So we just want to know how we can permute these. Why 4 choices? There are 12 places. Yeah. Hmm. Hmm. Yeah, that's right. So one x has 12 places, right? Yeah. And yes, 12. Yeah, but 12 factorial, right? It's 12 factorial. No, but you're on the right track. So see, the way we had done that previous one, right? We just asked that in from 12 places, we want to select 4 places for x. That's all, right? So step 1, as you guys are taking only choosing one place for, sorry, you're choosing place for the first for one of the x's, and then you do that for the next x and so on, right? But you can do it at once. Yeah, you can say, you can ask how many ways to choose 4 places for the 4 x's. That's all we need to do, right? From the 12 places, we need to choose 4 places where we are going to put the x's, right? From 12 places. So how many ways can we do this? Just this particular step. Step 1. This is not the answer, because after that 8 places will be left and then left to think. But first, no, we have to choose 4 places from 12 places. Yes, exactly. It's 12 choose 4. Just 12 choose 4. That's it. So it's just the concept of choose. So see, all these places are distinct. Think about that, right? The places are distinct. This first place, second place, third. Yeah, you guys should not get confused with this. The x's are all the same, the y's are the same, and z's are the same. But the places are distinct, and you want to choose 4 distinct places from 12 distinct places, right? 4 distinct places from 12 distinct candidates. That's it, right? That's all it is, right? It's the same thing. So this can be done. So maybe I just remove this now. Some space. Still choose 4, right? So now this formula is coming to light. But then next steps, and think. Yeah. So this is 12 choose 4. It is simply 12 choose 4 and nothing else. Okay. Now, what should we do next? For what will be the answer for y? How many ways? Just how many ways? 8 choose 4, right? Because now only 8 places are remaining. That's right, absolutely. And this way we are covering all the possibilities. Yeah. How many ways to I'll just let's write it. First time, 4 places for the 4 y's from 8, 8. And that's 8 choose. Yeah, that will just be 1, right? Because whatever 4 places are left, but yeah, but that's theoretically that's correct. Okay. So it is just this. And so what should the answer be? 12 choose 4 times 8 choose 4. Because for every choice you're making for the x's, you make, yeah, for every choice, for every 4 places you choose for the x's, yeah, in any of these 12 choose 4 ways, you have 8 choose 4 choices for the y's. So for every choice it's there, and so it multiplies, right? Because there are 12 choose 4 ways, many ways for choosing. So each of these dots is a way, right? So it may be that you choose 1, 2, 3, 4, or it may be that you choose 2, 5, 7, 9, or something else. For each of these ways you choose for the x's, you have 8 choose 4 for the y's, and 8 choose 4, and 8 choose 4. So, and you understand, just multiplies, obviously, but so yeah. So then this is the answer. So then is this wrong or is it right? It will not match, or will it match? Let's work it out. Can you just work it out and see if it matches? And that also leads to some very nice identities. So yeah, let's see. Try to see if it matches. So I don't want you can obviously calculate it, final answer also, but you can try to match it otherwise also. So just check it, just see. you see, it will come out to be the same thing, right? You see, if you, yeah, that's right. That's right. Yeah. And that cancellation is a very special thing. It's not a coincidence that it is canceling. Okay. It will always, in this kind of questions, it will always cancel. That is the idea. Okay. So yes, so these are the correct, these are the same things. We don't have to calculate and know it, but they are same on a deeper level. That's what this is. I mean, it's not a coincidence that they are the same. They are the same. Okay. This is what it is. So I think this was a three-dimensional and three-dimensional analog that I wanted to do. Now let us move to let me just state the result again. Okay. So number of ways, and let me not define more things like multinomial coefficients now, but just state this. Okay. Number of ways to go from 0, 0, 0 to 1 second. I think my battery. Yeah. 1 minute. Just plug it. Yeah. So the number of ways to go from 0, 0, 0 to, in general, if it is m comma n comma p, right? Then obviously one answer is this. I mean, there is only one answer, but yeah, it's what we already did. But the other answer is what? The way you will do it is you will say, okay, there are so many places. I will choose m places for the x's. Then out of the remaining n plus p places, I'll choose n places for the y's, and then p choose p, which is just 1. Yeah. Just take some numbers and check it also again. I mean, but is this okay? This is what we will get, right? If we apply the method, this is just a, you could say to begin with, a guess or a good analog extrapolation. But this is what it is. But then if you check it, if you actually, write what this means, I mean, sorry, write what it is. I mean, what the formula is for this, okay? Then you will see that they are the same things. Okay, you can check that. So this is a very rather interesting result. Okay, which again also says that a number like this will also be an integer, which is not very clear. It's not obvious number theoretically that this is an integer. Okay, but it is an integer. Okay. Yeah, let me now do a very standard question. Okay. Yeah, let's try to do it and then we'll see if it is related. Okay. Standard question. So this is, I could say this is like permutation with repetitions. Okay. Permutations with repetitions. But we will see if we can approach it with the way we have been doing things. Okay. So I can just take a very standard example. Okay. Number of ways to jumble up or permute the letters of the word Mississippi. You may have seen this question already. If you have opened up NCERT ever in this chapter, you would have seen it. But in any case, let's try it. And also we will do it in a different way, maybe from, yeah, let's see. Just think about it. Just give me a minute. Yes, and you guys have seen this question? Anyone else, two of you have seen this question before? No, okay, then it's good. Yeah, but this is one of the standard questions. Usually the other stuff we did is not like it's not standard, but this is a standard question. Okay. So we want to see how many ways we can. You see, you guys obviously understand that the if there is any problem in this problem is that there are repetitions. Yeah, that's why the topic is because if there were no repetition, then it will just be that many factorials. Simple, but there are repetitions. Yeah. Mm-hmm. Yeah, but then the S's, it, how would you say? Yeah. So if I say that for M, there are 10 places, so there are 10 choices. But then which I, that's the problem, right? Which I are we talking about? We cannot say this I has 9 choices, right? Because these two I's are considered the same because, right? Because if I put this I here in the fourth, in the, right? If I place this I in the second place, or if I place it in the fifth place, I'll get the same answer, right? But I will be counting it as different. Is that right? Yeah. Why? Why? Hmm. Yes, yes, you've got the idea. Right, right. You've got the idea. That's right. The three-dimensional analog that we did, it is just very, very similar to that, right? This is like, this will be what dimensional? This will be like, so four, yes, absolutely. This will be four-dimensional, right? Because here there are four kinds of moves, right? There is a M, there is a I, is that right? And there is a S. Sorry, and then the P, there's a P. So there are four kinds of, so this is like a four-dimensional thing, but we don't have to worry about all that. We can just do it by the same method. We don't have to formalize this as a four-dimensional lattice problem and so on. Simply, so yeah, so let's do it using the chooses. I think you guys have got the idea, but let me do this because it's a standard question. That's so you should know how to do this. That I should do it, and then there are many other interesting variations of this. Okay. So you see, it's a very interesting thing that we are able to do it. Otherwise, this is a it's a topic of its own, and there is a formula which proof is not very clearly given. Or yeah. So basically, as you've said, we basically choose places. Yeah. So choose. So I'll just write it in steps again, just the way so that you know if you do things, different things, and but if we're able to do them in a similar way, then it's better. I think. Step one. So we just what we do is we choose one place for M, right? From how many places? 10. Okay, yeah. 5, no. 6, 7, 8, 9, 10, 11. From 11 places. Yeah, 11 places doesn't matter. Or maybe, yes, 11. Yeah, okay. Then step 2. So now maybe someone can come and say, what exactly should be step 2 in the way we're doing? No, not for M. For M, we have already done it. Yes, no, there are 4 I's. I mean, yeah, there are 4 I's. So yeah, that's what it, right. So choose, yeah, that's right. So choose 4 places for I's from 10 and so on, so on. See, this becomes a very simple question. Otherwise, this is a topic. It's also called permutations of multisets. Brualdi says it as multisets. That's the right language, which is used, which is very nicely used later on also. But yes, so in this way you can do and you will figure out, please check it. Okay, please check it. Okay, don't just remember this formula, but just check it, that you will get 11 factorial. And obviously, let's just do it, yeah, in the way. And it's quite sad that usually it is just written as a formula like that, and just not like this. This is how it should be written, because this is the way it actually comes, right? The way that you guys are doing, it's coming like this, right, in a very natural way, as if you're just discovering it. But usually, if you see it in the book, it will be written 11 fact in the board level books. They're 4 factorial, and then they will write another 4 factorial and 2 factorial, which is cool. It's okay for remembering, good enough for remembering, but this is actually how it comes. Yeah. And then we have 6, and we have 6 choose 4, and then 2 choose 2, I think, something like that. Something like that. And this. Okay. So from this, you can actually understand the entire process. What happened? You know the entire thing. What happened? Okay. So yeah, this is what it is. And yes, so this is what I wanted to do. Okay, I'll do the other variations next time maybe. Okay, now we will continue, but now I'll do some variations of the lattice problem. I won't want to do the easy stuff anymore. Okay, I'll just do slightly more interesting stuff, and then we'll see where we can go from there. Okay. Yeah. Yes, so let me just start with one variation. Okay, let's do a variation which is not actually a lattice variation. Okay, let's just do this one. Yeah, so this does not look like a lattice path problem at all, but let's see the problem first. So here we have yeah, let's say we have 12. 1 minute. Oh god, someone was trying to join and I don't know, I didn't decline him, but somehow it just went away. Okay, so there are 12, let's say 12 distinct balls. Okay, 12 distinct, sorry, 12 distinct balls. Okay, and we have 3 distinct boxes. 12 distinct balls and 3 distinct boxes. Yeah, we want to find the number of ways to put these 12 boxes, 12 balls in 3 boxes. Okay, to put, yeah, so to wait, let me not say it like this. Number of ways to distribute. So again, just let me repeat, this doesn't look like a lattice path problem, but you see number of ways to distribute such that box 1 gets 3, box 2 gets 2, and box 3 gets 5 balls. Yeah, let's think about this. Let us see how we can do this. Yeah. Mm. Yes, so they have to be some 2 balls have to be outside in every case. Yeah. You can think about it, but no, yeah, that's something that you should think about. Yeah. Just try to use the formula. See, I mean, otherwise the answer should be 0, right? The answer should be 0. Because if you take the definition of choosing, but if you take the formula, then you can see what you get. So just try to take some numbers and try to write the formula and into n minus 1 and so on and see what you get. Okay. Yeah. So yeah, anyone, especially those who have joined also, if they know how to do this problem, especially if you can connect this with lattice paths. Obviously, some of you may just know this, but in any case, yeah, how would you do such a question? This is the most standard version of balls into box question, and this comes in many guises, various. So there are 3. So start drawing a little bit. Box 1, box 2, box 3. Number of ways to go to 3, 2, okay, from 0, 0, 0. From 0, 0, 0 to 3, 2, 5. Okay, so why are they related? Yes. Yes, that's an interesting correlation. Yes, the moves are, as we know, only either in the x direction or y direction or up direction. Are these the same questions? So this is just the question. Okay, we do not know if they are the same questions yet. It's a claim. That's an interesting connection. Wait, 1 choose 5 or 12 choose? No, you mean 12 choose or 1 choose? Okay, no, you're thinking like, no, it's not 1. Yeah. I mean, that's obviously wrong. You can also understand. Yeah. Yeah. Yes, that's what it is, right? So when you do 12 choose 3, so it's a very simple question, right? You guys can see is 12 choose 3. So what should we do next? Anyone? What should be the next thing? Yeah, right. Exactly. 9 choose 2, and then you have 7 choose 5. But this is slightly different from the lattice path thing. It's not the same question. And that's because 2 boxes are remaining. Yeah. Sorry, 2 balls are remaining. Just let them be. No worries. But this will not be the number of ways of going from here to here, right? You can calculate. Obviously, you guys know how to do this. You can see that it's not the same. Okay. Had there been 10 balls, had there been exactly the number of balls as needed, then it would be this. Okay. This will not be exactly. Yes, that's another. Absolutely. Yeah. So that's another interesting way to do. That's what I was thinking someone would say. That's right. Then you can look at it as a 4-dimensional analog, okay, where you have to make 2 moves in the 4th dimension in the whatever W axis, right? So it will be like this. Okay? Then they are the same questions. Yes, that's absolutely correct. No, this is not 0. Why will this be 0? No, it is not 0. This will not be 0. Yes. You can leave. Yeah, that's fine. Okay, so that's a little strange, but that's what we have to do in this question. In the sense that that's what the question is asking. Yes. And you will get an answer. So this will be, as you can understand, this will be 12 factorial, 3 factorial. So you have to just work it out. 2 factorial and 5 factorial. That's right. This will be the answer. So this will not add up to 12 factorial. But if you add a dummy box, then no. Wait. This is wrong. What I've said is wrong. There'll be another 2 factorials. Work it out and you will see. Right. And the more interesting, the more if you do is just say that you can add a dummy box. So the balls that you're throwing away, you can imagine that there is a 4th box in which you're putting them. Okay. So yeah, and obviously this formula we also saw through lattice paths. I didn't do it for everyone, but you guys know that this is, yeah. Okay, that's a simple question. Okay, now let me do a variation of the lattice path problem. Okay, yes. No. See, there will not be, but it just comes out, right? It just comes correct. The other will be 2 choose 2. Right, but that's just 1. Yes, that will just be 1. Yeah. So, and also because we did this, because we already did this question in this way and it's correct. Yeah. The dummy box is just another way to do it. Okay. Now let's do a variation. Yeah. So a variation. So we're just trying to do variations of these kind of question, variation of lattice path problem. 1 second. Yeah. So let's do this variation. What was the variation I was thinking of? Yeah. So here we want to start from 0, 0, okay, end at 0, 0, okay. The allowed moves, so allowed moves are obviously all the 4 moves, and these 4 moves, okay, these are the allowed moves. Okay, so this is the allowed moves, and yeah, let me mention this, and 100 steps are allowed. 100 steps in total. Let's see if this, because it's just a question, just made up, should be possible to do. Let's see, 100 steps in total. How many ways? How many paths are there? Can you explain us? Yes, that's right. Yeah. Yeah, so that's all you need to do. That's right. Yes. So number of ups, yeah, this is very easy. Number of ups equals to number of downs, and the second is, yeah, number of rights is equal number of left. And now that I think about it, I think this is a problem from some I think it was there in desktop mathematics also. I think, yeah, I didn't make it, so just I think it's coming in my mind, but yeah, so this is all you need to do. Okay, and then this just reduces to, so no, but the question is how many no, but how many ups and how many downs? How do you decide that? Yes, that's what I am also thinking. But someone said that it will be, it will not be so easy. There will be some kind of a summation. Okay. So let's just give us a minute and think about this. Let's everyone just try to build on this and see if we can answer this. Yes. But these two things are obvious, right? These two things are obvious because you want to come back to zero. And but you have 100 steps in total. No, but you have only 100 steps in total. Yes, yes, that's what it seems like. But can you think of a way to simplify it? That's the challenge. Is there a way to? Yes. Yes, they have to be equal in number. But see, there is no way to know how many ups and how many ups and how many rights is there, right? But not fixed. Yes, but they're not fixed. That's right. Yes, that's exactly what I'm saying. Right. They're not fixed. So yeah, but there should be a more direct way to do it. Let's just do it like this then. So if it's not fixed, then as saying, if we take cases, okay, we take cases. So we take case one, 0 ups, okay, 0 ups. So they don't go up at all, only go right and left. Okay, what should be the answer in this case if there are 0 ups? That's right. Then it will just be 100 choose 50. Is that right? Yes. Right. This is just like the old problem. No, this is correct. Yes, right, because you just have R's and L's, just an arrangement of R's and L's, right? 50 R's and 50 L's, 100 choose 50. Right, so then similarly, we can do 1 up, yeah? Then it will be how much? Then what should be the number of ways? If there is 1 up, yeah? If there's 1 up, then you have 1 up, you have 1 down. Yeah. And you just what does it matter? No, so the path will be the entire journey, right? No, there are 0 up moves. So R moves. Yes, yes, yes. So by path here, I mean the total journey. Yeah, the total thing, not just the final path that is traced out. Okay. So yeah, so you have 1 up and you have 1 down, and then you have 49 rights and 49 lefts. Yeah. So how would you do this? So again, you can just work it out. It will be a little complicated. But make it more precise. Yeah. But I don't understand what you're saying. That is something that we all know, but Can you say something more precise? I mean, how do you combine them? What do you mean by combine? That I don't understand. Like, is it different from doing the casework? It is the same thing, yeah. Like it is, that's the general idea. But in this way, you see, we'll do a lot of casework, but eventually what do you do? That is the thing. Yeah. But there is a way. There is a way, certainly. I can see an answer, but yeah. Please say someone has an idea. Right. X ups and Y rights. X plus Y. Yes. That's right. That's right. That's right. But this is again just what we are seeing. Yeah. So then it will be x factorial, y factorial, right? Because if x. No, both will have square. Why will it not have square? Because no, but if you work out the formula, that's what it comes out. Yeah, just that's a small thing. Just work it out. You have x ups and x downs, and you have y lefts, right? So you know that if you have four kinds of things, right? I mean, number of u's, maybe you can just say this, number of, 1 second. So you have x u's, y d's, and then, no, sorry. Yeah, x u's, y r's, x downs, and y l's, okay? So we all understand now that if there are four kinds of things, right? U, R, D, L. This is like a four-dimensional analog of problem, or any other way you can see. Is it okay with everyone? Yeah. This x, y, x and y will be different numbers, okay? But you can understand. Then the number of ways to permute them will obviously just be this. Yeah. If you have x u's and you have y r's and so on, then this will be the number of ways to permute them. Now see, the point in the end is that I guess some of you who have done some advanced binomial coefficients will understand that this summation, this will be a summation, right? Because it can be summed easily. Like I'm not interested in the answer, but what I'm interested in is a more direct proof. So this thing, obviously, so I'm just writing summation notation. I'll also expand it and write it, is that x goes from 0 to 50. Yeah, that's what happens in the summation, right? So just to write a few terms, this is what it will be like. So if we remove this part, but eventually you'll get a very crisp answer. Now the challenge is to get that answer directly. Okay, we'll not do that now, but just think about it. This thing, you see, literally what it will come out to be is 100. And we already have this one case, right, where it is 50 factorial. Yeah, this is case one basically. And then when you take 1 factorial, 1 factorial, 49 factorial, 49 factorial, like this and so on, right? The x will increase, the y will decrease, and blah, blah, x will go to 50. Okay, so is it clear to everyone this is what the answer will be, right? But now some of you can use the power of summation of binomial coefficients, formulas, and so on to get a better answer from here. But we want to do this problem in a better way without so much casework. Is it possible? I do not know. Think about it. Yeah. I want to improve the answer by changing the way of the problem. Yeah. So not by summation, because that's obviously then it's not bijective proof. That's not combinatorics. That's more like summations. Okay. So the final answer will be interesting. It will be this. Maybe I can say, and then you can also think. It will be something like, what will it be? No. That's right. But eventually, what it will come out to be is 200 choose 100, something like that, right? Something like that. I do not, one has to sum it up. Is that correct? Are you sure? No. The final answer. Okay, let's see. Yeah. Right. So in this summation, if we make some manipulations, yeah. But in any case, let's not do that. Let's you guys think about how to do this directly to get a good answer. Okay. So do this without casework. Okay. Do this without casework. That is the challenge. So this can be done without so much casework. Try to see how you can do it. Bijective proof. Okay. Slightly challenging. Think. Okay. So let me now do a easier question. Okay. This is also easy, but it's an easy question. Suppose now you're starting from 0, 0. Okay. And again, now the moves, now you have two moves. Okay. Two moves. Hold on. Yeah. Okay. Two moves. You have this and you have up. Okay. So two moves. And 100 steps. Right. So the question is, what are all the different paths that one can, one can take? This is easier question. Let's think about this. So I'm looking for the different paths that you can take. So there is no specific place where you have to reach now. You want to start from 0, 0. Yes. Why? No, it's more easier than that. There are two. Yes, that's right. Right? Think about why it is 2 to the power 100. It is just 2 to the power 100. Yes, right? It's just this simple. Yeah. Yeah, you can just do, you can just do anything, because now there are 100 places and you don't have to fill some number of rights and some number of ups. You can just do anything. So this is just a very silly question, but just in this context, it is there. Yes. You see, that's an example, right? You can also do this by casework. Now, if someone doesn't spot it, then they can do this by casework, right? They can say, okay, I'll take 1 right and 99 left, and then blah, 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 and it'll take a long time. And then you have to do a summation. But we could do this directly. Similarly, the previous question can also be done directly, but think how we can do it directly. All right. Yes, so this is a thing. Yes. Okay, now there is a certain question that I wanted to do, which is related with what we had done earlier. So this is something that is just left out. So I just want to finish it. Okay, maybe. No, it will not be 4 to the power 100. That is too much. No, it will be still something, choose something in the end. Yeah, the summation is very specific. It's not, that's too much. 4 to the 100 is too much. I mean, most of the times you're not going to come back, right? The probability is 0. So 4 to the 100, that cannot be the answer. So it's too much. Yeah. So yeah, the next question I wanted to do is some related with what you've done earlier. Okay, and this was a problem context. So yeah, so we have done this, right? The highest power of, so this is not related to lattice path, but just want to do it because it will be left out. Is highest power of a prime p in n factorial. Yeah, we know the formula. We know one formula. We know that it is this, and you keep doing it because at some point it will automatically become 0. So don't need to worry. Okay, but now we want to do it in a slightly different way. Okay, let us 1 minute. Yeah, let us just do this experiment and then we can understand it. Yeah, take a number n. Okay, take take any n you want. Okay, let's take it because so that we can all do it together. So let's take n to be 102 or something, 102. Okay, let's fix a prime p. Let's take p to be 13. Okay, or let's take it to be 7. Otherwise, the number is too small. Let's take it to be 7. Okay, first step, let's do the following thing. This is also 2. Okay, write n in terms of powers of in base 7. Okay, in terms of powers of 7. Okay, I mean, this is something that we have all seen in different places. Let's try to do this first, and then you see the connection. In base 7, yeah. So we want to write 102 not as powers of 10, but as powers of 7. Okay, so now you guys can see how to do it. You can check how to can try to do if you have not done it. Yeah, 204. Yeah, you can immediately check it. So it is no. Or am I going to say 204? 204 doesn't. Oh yeah, that's right. It is right. Sorry. Yeah, you see this is just does it right because it is 102. Okay, so 204 is the thing. Okay, now consider the number n. Okay, so 102 is 204 in base 7, right? You can write it like this. This is base 10, but in anyways, now let us take the sum of the digits. Okay, let us take the sum of the digits, that is 2 plus 4. Okay, so sum of the digits in base 7. Base 7 is nothing, just as I've said, powers of writing it in terms of powers of 7, and the coefficients become the digits now. Okay, just the number of times you need to take that weight and so on. Okay, sum of the digits in base 7. So yeah, so you want to know sum of the digits in base 7. What is it? It is 6, right? It is equal to 6. Okay, now we take 102, we subtract this 6. Okay, and then divide by p minus 1. Because p minus 1 is 6 here, right? So 102 minus 6 by 6. So what does it come out to be? Just base 7 and base. Yes. So this is C, as so I talked about this in the class, right? When you're saying writing a number using weights, right? So yeah, I mean base 7, base 10, yeah, it's just like that. I think it's good for all of us to understand this very clearly, because you see, we know how to do this maybe, but this just means that you write it as powers of, in terms of powers of 10, right? So you write it as 10 square plus, obviously, you know this, 10 plus 2. This is what it is. Okay. Now, the next thing we would write to do is you write it in terms of powers of 7. So when you write it in terms of powers of 10, then the digits, then the coefficients you get are your digits in base 10. That's the way we learn things, right? But when you write it in terms of powers of 7, then the coefficients that you get become your digits, and that's called base 7. Base 7 is just a name. Base means that's the base. Those are the base weights. Base weights that you have is 1, 7, 7 square, and so on. Using them, you try to make up the things. It's very remarkable that every number can be written uniquely in a particular base, and so on. Yeah, but all that we have seen, right? So then this is what it is, and then you just, yeah. So then what will this be? So I'm just taking the number, writing it in terms of powers of 7, taking the sum of the digits, and then doing this. Okay. So then what do we get? Minus 1, it is 16. Okay. Now let us try to find the highest power of 102, highest power of 7 in 102 factorial. Let's try to find out what that is. So highest power of 7 in 102 factorial. $16. Yes. So you see, it will come out to be 16 only, right? Now, how do we explain why are these? Because these two look, maybe they look as very different things. Yeah, we did some very different things, right? Here, so yes. So 102 was a number, right? This was a number that we started with. Then we said you take the number, you write it using powers of 7, and you take the digits you get in that case. These digits. You take the sum of the digits and you subtract it. So this is the sum of the digits in base P, in base 7 here. And then you divide it by P minus 1. P was the prime. Okay, this is what we did. It looks like a very strange thing to do, right? But let's say we did this, okay? And if we do this, then we get 16 as the answer. And this matches the highest power of the prime 7 in 102 factorial. Okay, so P was some prime, right? We first found the highest power of P in n factorial by this method. The usual method also you get 16. But this other way we are doing is also coming out to be 16. Why are they the same things? Okay, so in general, you take a number n, you write it in base 7, and you subtract the sum of the digits. So you write it in base 7, the weights you get, those are your digits. Subtract the sum of the digits, divided by P minus 1 by 6. And this turns out to be equal to this. So we want to explain why this is true. So first question to everyone is it clear what we have done? Okay. One of them is just finding the power of the prime P or 7 in n factorial in the usual way. But the other is a slightly strange thing, right? N minus some of the digits in that different base divided by 7 minus 1. So why are these two things the same is the question. Also, still, if it's not clear what exactly we have done, then please tell me. Okay. Yeah. Then we can try to explain the prove why these things are equal. Okay. Yeah. Let's see. So it's a very curious fact, right? It's a very strange thing that has happened, but now we want to explain it. We want to give an explanation that will work for any number n. Okay, so let me, yes, yeah. Okay, because of some of the digits. Okay. No, but this is a little different because for different prime and 9 is some of the digits and 9 are obviously very related things and a lot of questions. But yeah, in any case, yeah, let's try to explain this. Okay, it's not hard. I guess if you guys given the time can maybe do it, but let's just do it. Okay. So see, what we are trying to do is we are trying to show that, and please, if you're not comfortable with this entirely, take examples. Okay, this is obviously in the level 2 part, but take examples and do it. Okay, just whoever is see, take examples and just take a different prime, do the same thing and just try it. It's a very, at least to check it, it's very easy. Proof is even easier, you see. Okay, I'm not going to literally do much. Okay, and it'll just come out. So 1 second. Okay, some yeah, so maybe she's joining from 1 second. Okay, cool. So we are looking for the highest power of prime in n factorial, and we know that it is this. Let us just take it to be 7 for the time being. Okay, let's take it to be 7. So just like this, just goes on like this. Okay, now we want to show that this is equal to, again, it's very strange maybe, but you'll see it's not strange. N minus sum of the digits when you write n using powers of 7, some of the coefficients, divided by 7 minus 1, 6. Same thing. Why are these two the same things? Yeah. So, yeah, let us see. So, let us just try to look at what n looks like. Okay, I mean, in general, I should not even say it looks like. When you write n in terms of powers of 7, then how do you write it in general? Okay, but I still just use this phrase. What n looks like, it looks in terms of powers of 7. Okay, so let's take n. Let's say you wrote it in terms of powers of 7 and you got some. Okay, some things like this. Right, ak minus 2, 7. So these AKs are the digits, right? So this is the general thing I'm writing, meaning that in the previous problem, this was 2, 0, and 4, obviously, but here I do not know what it is, so I'm just writing it. Okay. This is A1 times 7. Okay. This is A0. Okay. This is how it will look like, right? If you write it, when you write it using powers of 7. Now, can anybody, now meaning that guys, some of them already have done it, how can you relate this with the left hand side somehow? This is exactly what n is, right? And S7 of n is the sum of the digits or the sum of the coefficients. Yeah, same thing. Okay, so our goal is to somehow bring this in the picture, right? How do you do it? You see, if you say n by 7, right? If you say n by 7, what is n by, and you say n by 7 box, floor of it, right? What is n by 7? N by 7 is nothing but 7 to the power k minus 1, k minus 1, 7 to the power k minus 2, and so on. You get a1 plus a0 by 7. Yeah, very clean. You see, now when you take the floor, then you will realize, aha, the basis is actually the right way to think about these floors. When taking the floor of a number, meaning on the integer part of it, actually writing it in that particular base, whatever you're dividing by, is the right way to see it. Is the right way to see the number. Then it simply becomes this, right? That's all it is, right? Now from here you understand what to do, right? If you now take n by 7 square, so this thing and then this thing, and then I'll add them and write it using bases. We are already doing that slowly, right? So you see, now you guys can try to finish it from here. Okay, it's a little abstract to do it if you have not done too many proofs, but those who have done will. Okay, but all of us can check this fact and appreciate it. It's just be a2, because the a7 by 7, right? When you take the floor of it, this is less than 1, so that becomes 0, and the others are integers, right? So they will remain. That is the beauty of it. And this way you can do it. Just keep adding them, right? So now when you add these numbers, you take this n by 7 and you do this n by 7 square and by 7 cube and so on. Do this, right? Then what is it that you're going to get, right? You are going to get right. So what will you get? The a1, right? The a1 you are going to get 1 minute. Yeah, now it is just a matter of summation and so on. So how do we say this nicely? On, yeah, maybe we can just say this. Yeah, so you're going to get a1, that's going to be once, right? Only once, right? Because in n by 7 square there is no a1. Then a2, how many times are we going to get the a2 and with what coefficients, right? So the a2 in n by 7, the a2 that you get will be 7 times a2, that's 7. And the next time you get it in n by 7 square, the a2 is just with 1, right? So you see, you can just work it out now. The details are not difficult. Then the a3, the first time you get the a3, it will be with the 7 square in n by 7. The next time that you get it, it will be 7, because here a3 will be 7 times a3 somewhere here. And the last time you get it in n by 7 cube will be just with a 1, right? And in this way, you can keep going. This will be 7 cube, 7 square, 7 plus 1, and so on. With A5, you will get this. Okay, and so on. So it's now very simple. You can just finish it. So yeah, let's just do it. Okay, so this is 7, this is A1, and this is A2. So this is just, but the way it should be done is, it is 8, but obviously, but we will say it as 7 square minus 1 by 7 minus 1, right? This is the geometry progression formula. So I'm just using a formula. You see this summation is just 7 to the power 4 minus 1 by 7 minus 1, and so on. Now you guys can see how it is coming, right? This goes like this. This is still the highest power of n, right? And that number, okay? Still just that, okay? But now you see it's very clear, okay? So you can also just do 7 minus 1 by 7 minus 1. Now it's all very clear because it is just there. The 7 minus 1 is just there in the denominator, and the 7 times A1 plus A2 square and this so on, this will become your n, and the rest minus A1 minus A2 minus A3, that will just become the sum of the digits. And there's a A0 which you can add subtract, so it just comes. Okay. It's a very simple theorem, but if you just write it, if you just write these things, this base 7, what it is, and then just keep doing it, arrange things, and just, it's very easy. Okay. It's easy, but it's a little abstract. It's a little, not done proofs. So, okay. Yeah, but this is a very interesting fact that we should know. We'll soon see we'll later on see other ways to find highest power of prime and factorial. Yeah, in maybe other interesting ways. Okay. There, yeah. Yes. Okay. But this basis will appear there also maybe. Okay. So that's what this is. And yeah, let me now move to some more. Yes. Yes, sure. No, yeah, you can leave. So now the next question that I wanted to do is, yes, so here is a question which is again about counting walks. This is interesting maybe. So we have 8 vertices, yeah, 8, doesn't matter, you can take 6 only. Take 6 vertices, okay, and yeah, so you have 6 vertices, and you are going to move on these. Okay, so the move is that each step can visit one neighboring vertex. Okay, can visit one neighboring vertex. Okay, so if you are here, you can either visit here or you can visit here and nowhere else. Okay? That is what it is. Okay, either clockwise, anti-clockwise, any one visit. We are initially at A, and B, C, D, F. Yeah, vertex, and let's say that we have 111 steps. Okay, 111 steps. Okay, so the question is, how many ways, okay, how many paths from A to D? Yeah, so if you want to understand how many paths are there from A to D, yeah, just think about this. Give me 1 minute. I just 1 second. Yes. So in so many steps, we want to know how many ways are there. Yeah, you can go both the sides and you can do it in many complicated ways, right? So yeah, you can, so you can also like go to B, then you can come back to A, then you can go to E to F to D, you can go to D and then again come back. You can, so we want the entire sequence of steps matters, obviously. And we want to know how many ways. So this is again walking on a graph cycle, and you want to understand how many walks will be there. Okay. Yeah, you can do that. Yeah. Okay. Okay. That's right. Yeah. So maybe we can mention that, right? So yeah, so we can mention it like this. Maybe there are two ways. Okay. So either three extra. Yeah, that is an interesting feature. And in fact, you can use this to prove a more general version later on. It will be useful if n steps are given, then this will be particularly useful. Okay. But in any case, let's just write it 3 extra clockwise or 3 extra anti-clockwise. Oh, yes, obviously. So what I've said and what you have said was earlier wrong. Yeah, that maybe you could consider as a 0, but yeah, obviously. Yeah, so that's wrong. Yeah, that's right. Yeah. So, but it will always, you will always need an odd number of steps. Yeah, you can't do it in an even number of steps. Is that, I think that is something that is a good thing that you can try to prove. Okay, will always need an odd number of steps. Ten plus 3. Uh-huh. No, that's too much. I don't think that is correct. Just being odd is enough. You can, or yeah, I think just being odd is enough. No, 6n plus 3 is there, but I think that it doesn't need to be 6n plus 3. 6n plus 5 will also work. No? Or let's see if there are, so you can go 1, 2, 3, 4, 5. Right? So you can go from A, B to A to B to C to D. There's 5 steps, 5 edges, 5 moves. No, I mean, you only need an odd number of steps. That's all. 6n plus 3 is not necessary. And that is easy to prove. That even number of steps cannot be used is easy to prove. Yeah. But the real question is how many paths are there in total from A to D? And how do we do this? Yeah. I mean, you can obviously prove by induction also that odd number of steps will not be enough. How? What is that? Yes, that is the difference. Yeah, there is only one difference. Hmm. No, no, no. So the number itself, the number of this move and that move, I do not think that it will be enough. The number of directions, the number of moves in some direction, other direction, that will not be enough, I think. Or yeah, because it's a circular thing, right? So yeah. Yes. How do you use recurrence? So A, you can go to B and return to A. Yes, yes. Yeah. Okay. Yeah. Right. A to E. Okay. A to E. So what is BN? E to D? Okay. Okay. Yeah, that is the same thing. That's right. And similarly, yes, that's good. That looks good. However you go, you'll reach at D. No, that's not correct. Yeah. Hmm. Right. Right. Hmm. No, but I mean, how do you know how many clockwise and how many anti-clockwise? So, okay, I mean, if you say like that, then no, that's so you said that you have X clockwise. Okay, X clockwise. No, see, 111 steps, you're not going to reach D. Okay, simply, I can give you an example. Okay. You can just go back and forth between A and B. 111 times, you will reach B. So certainly that's so. I've not found a problem in your argument, but certainly it's wrong. The conclusion is certainly wrong. Right? Because I can just go back and forth between A and B. I'll be at B after 111 steps. So the recurrence is the right way to do this problem. Okay. And that's what I wanted to come at, today. That last time also we set up recurrences. So today also we just want to set up recurrence for this, and then we'll see what to do. Okay. And today I'll not go up till 10. Okay. I just go a little slow because there's something in the schedule which has got I need to fill in. Okay. So, but we'll set up the recurrence for this before. Okay. Next time I'll make it up. I plan to do a 90-minute class, but we'll just do a 60 minutes class. Yeah. But now, how do you set up the recurrence? So we know this variables. It is good to set up a recurrence and so on. Let's see. Yeah, you're right. Right. Yeah, that should be even, because obviously, and also, I mean, you do realize that also that we need to mention number of paths for me to be in 2n steps. Otherwise, there are infinitely many paths. Okay, and this will be you can just take this to be some odd number. You can just take 2n plus 1 in 2n plus 1 steps. But then what? Even number of steps. Yes. No. Is there? Okay. Why? No, I don't agree. But why? So in 2n minus 2 steps, if you reach from A to C, how does that give you a way to go from? Yes, I mean, so this will be part of the answer, right? That yeah, you reach here in 2n minus 2 steps, then you go up and you go down, and in 2n steps you reach there. Or you can go to D and come back. But that is, yeah, but that is not the only way to do it, right? Is that the only, is this the, I mean, is this the only way to get to C in 2n minus 2 steps? No, but that is taken in this, right? I mean, that is taken in this, right? So you have to imagine. So if I think maybe it's correct, actually, I think from A to C, if you're going in, if you want to go to A to C in 2n steps, right? Then you will ask that, okay, in 2n minus 2 steps, where was I in the 2n minus 2th step? But the problem is that in 2n minus 2th step, this is wrong, because in 2n minus 2th step, I may have just been at A. Is that right? Yes, and also, I mean, if I'm at A, then from A, I can just take 2 steps and go to C again, right? So in the 2n minus 2 steps, I may not be at C. So this is incomplete. It will be more than 2 to the power n, right? What will it be? How do you set up the recurrence? So please think about this, okay? And it's not hard, but I don't want to say it, okay? In the sense that there are many ways to do this, maybe, okay? So think about this, and the hints are, okay, don't be afraid to introduce more variables. You may be looking for a very crisp solution, maybe, or you're not used to having so many variables in the recurrences, okay? But you can introduce more variables if needed, and then, you get a system of recurrences and eliminate. Yeah, just solve a system of solve, meaning that I'm not saying you should know the formula eventually, but at least in the end, you can get a simple recurrence at least. And you can apply the formula if you know it. That's not the point. And then finally solve and simplify, I should say, and get one variable recurrence. Okay, so please just do this. Okay, just do this for me. And yeah, I think so. I did plan to do other things, okay, but today I will not be doing. Today I will not be able to do. I have some other commitment. Okay, yeah. So yes, so that's it for today. And next time we will meet on Wednesday, or rather, yeah, the Tuesday's class that we're having, right? That we'll probably do on Wednesday only. And maybe we'll do both the analysis classes on Wednesday, or one of them Wednesday, or one on Friday, something like that. Okay, I'll tell you. Or we can do on Tuesday also. I'll mail. We'll continue that monotonic sequence thing there and so on. And then the usual analysis class that we're having, that we'll do, and so on in the graph theory class. Yeah, okay. Okay then. Thanks. Let's try these. Today's class was slightly less material, I agree. But yes. Okay then. Thank you.